Hello everyone, my name is Zhang. I'm going to present our research work StochFuzz, a sound and cost-effective fuzzing technique for stripped binary. Green box fuzzing is one of the most important techniques for software testing and bug detection. By fuzzing, Google has found thousands of bugs. There are also more than 100 fuzzing papers published in top conference this year. Fuzzing is indeed a stochastic process which executes program with random input. Different from black box fuzzing, green box fuzzing can leverage runtime feedback to learn how to reach deep states during program execution. LibFuzzer and AFL, which are the most popular green box fuzzing tools, take the code coverage as feedback. Here are the typical workflow of LibFuzzer and AFL. In short, user use compiler to instrument the source code. After that, a stochastic process is performed where the fuzzer generates random inputs and the binary connects runtime code coverage to guide future input mutation. However, there is another situation named binary-only fuzzing. In that case, people cannot access the source code but only stripped binary. As such, compiler-based instrumentation cannot be performed, hence fuzzer cannot get code coverage as guidance. On the other hand, bugs in closed source program can also have serious impact. An effective binary-only fuzzing technique is critical for software security. Many solutions have been proposed for binary-only fuzzing. The first one uses dynamic translation engines such as QMU and PIN, which traps execution and translates the code on the fly. The method is sound but expensive due to the heavyweight machinery. The second one uses hardware support such as interpretive to connect runtime traces. However, these traces are generated at a very high rate and hence require substantial efforts to process. It is also difficult to collect runtime information other than counterflow traces. The third one is static binary instrumentation. It leverages binary analysis to do rewriting before fuzzing. Although it is cost-effective, some static binary writing is an undecidable problem due to the lack of symbol information. To achieve better fuzzing performance, we also choose static binary writing to enable binary-only fuzzing. Let's first discuss the challenge of static binary writing. The code on the left side consists of two code sections, code 1 and code 2, and an interleaved data section. On the right side, we present the execution traces, where the executed instruction, destination registers, and the evaluation result are listed in the first three columns, respectively. The last column presents the related section if the evaluation result is address relevant. The first instruction loads the address of data section into RAX. In this case, the address is 15. The second instruction loads an constant 8 from data section into RBX. The constant 8 denotes the offset between address 23 and 15, which we will explain later. Next, RBX is added to RAX. Note that the value of RAX denotes the address 15, and the value of RBX denotes the offset between address 23 and 15. The result will be 23, in other words, the address of code 2. An indirect jump is performed to jump to code 2 section, and then return. Actually, there are two fundamental challenges of static binary writing. The first challenge is to identify the interleaved data section. It is fundamentally undecidable. If we fail to separate data from code, we may rewrite this data as code, result in rewriting error. Additionally, this inline data increase the difficulty of finding indirect jump targets, for example, code 2 section. In addition, distinguishing between scanners and the address offsets is another undecidable problem. Considering the constant 8, we need to know whether it is a simple numerical value or it serves as an offset. Note that rewriting has no effect on a scanner value that is not an offset, but it may change an offset value because instructions may get shifted by instrumentation. According to our experiment, 3 state-of-the-art binary static rewriting technique all fails on some programs. The first technique we introduced here is named incremental writing. It is based on the insight that while green box fuzzer continue mutate input across test runs, they may as well be enhanced to mutate the program on the fly. As such, disassembly and static rewriting can be incrementally performed over time. Our basic idea is to trigger an intentional crash once an unresolved target is reached. Starting from the address where the crash happens, we can do incremental writing. Then we talk about how our technique handles the motivation case. Let's first assume that our underlying binary analysis can find the indirect jump target code 2 at address 23. We additionally assume we can distinguish code and data. Incremental writing starts by an initial writing step, which is to guarantee that the program will raise an intentional crash when it reaches an unresolved place. To do so, we patch all code as HLT instruction. Those HLT instructions will trigger a segment fault once executed, which denotes an unresolved target. In this case, the code from address 0 to 13 and the one at address 23 are replaced by HLT instruction. We additionally rewrite the address that we know for sure that they are instructions instead of data to a higher space with instrumentation applied. In this case, since the starting code address is 0, all the addresses directly reachable from address 0 must be called. As such, the first 4 instructions in the shadow are copied to address 100, and a jump to 19 is put at address 0. Observe that RIP plus 8 in the red box is changed to RIP minus 92 as the higher address. It is because we are trying to make sure that the evaluation result of each instruction unchanged before and after rewriting. Decided by this property, the indirect jump at address 113 will go to the original target address 23, which will trigger an intentional crash during a fuzzing run. It indicates 23 is a contraflow transfer target. The second step, incremental writing, is designed to generate a new binary which rewrite all the addresses that can be directly reachable from the crashing address. However, it is in general an undecidable problem to separate code and data. In previous example, the program will encounter an unintentional crash if we patch the data at address 15. To address the problem, we propose stochastic writing, which is driven by the following insight. As fuzzing provides a large number of opportunities for try and error, we can try different data and code separation, which leads to different binaries for different fuzzing runs. Over time, a large number of samples can be connected, allowing us to achieve the precise separation and correct rewriting. Stochastic rewriting is piggybacking on the fuzzing procedure. It is enabled by a probabilistic analysis for code and data separation. It will generate different binaries for different fuzzing runs. It can also locate and repair rewriting error on the fly. We will continue using the previous example to demonstrate how stochastic rewriting works. At the beginning, the probabilistic analysis is performed, where we compute the probability for each address belonging to data on the fly. As it is certain that the first 4 instructions are code, their probability are 0. Address 23 is uncertain, but it is likely to be code, so its probability is 0.1. Note that the analysis may be wrong sometimes. In this case, we assume the probability of address 15 is only 0.3. Based on the computed probabilities, we do initial rewriting. Specifically, we patch all certain addresses with HLT. For other addresses with small probabilities, we random select some of them to patch. In this case, we assume that we patch address 15 and 23. Note that we in fact generate many random versions. Different details can be found in our paper. As such, the program encounters an unintentional crash due to the mispatch. After that, we are going to check whether it is caused by a rewriting error or not. It is done by removing all uncertain patches and rerun the program. If the crash cannot be reproduced, it is a rewriting error. In this case, we remove the patch on address 15 and 23, and the program exits normally, indicating there is a rewriting error. Note that we ignore the higher space because they are less interesting. The next step is to locating rewriting errors where we generate multiple versions with different uncertain patches and observe their behavior. In this case, we generate 2 versions of binary. We observe that the crash can be reproduced with address 15 patched, but not with address 23, so that we can know address 15 is a data byte and address 23 is not. Most importantly, with such hint, we can refine the probability for a better rewriting. To enable effective probabilistic analysis, we propose a universal contraflow graph for disassembly. We present a simple example of UCFG. On the right side, we show the instructions decoding at each address. The first column shows the addresses, the second shows the byte value, the third shows the instruction size, and the last shows the instruction. For example, the first 3 bytes are decoded to an XOR instruction. Note that the green shadowed instructions are the ground truths. In other words, they are the real instructions. On the left side, we present the corresponding UCFG, where a load denotes an instruction and ages denote explicit contraflow. Note that it is a supergraph of the real CFG. Based on the UCFG, we develop a set of probabilistic inference rules to calculate the probability on the fly. For instance, one rule is for register use and define. In short, if there is a define-use relation between two addresses, both addresses are likely to be called. For example, address 0 and 3 read and write the register R6, so they are likely to be called. Another rule is that the control flow cannot reach invalid instructions or data. As such, address 5 cannot be an instruction because its successor is invalid. More rules can be found in our paper. Recall that we need to locate and repair rewriting error effectively. We leverage delta debugging to do so. In short, it is a binary search-like separation strategy, which enables some uncertain patch and then check whether the unintentional crash can be reproduced. We also address a number of practical challenges. Details can be found in our paper. Next, I will discuss the evaluation result. Our evaluation is conducted on 3 benchmarks, including Google FTS, a variant of Google FTS compiled with inline data, and the fuzzing benchmark from virtual write. We compare with 5 state-of-the-art binary-only fuzzing tools, including 3 static rewriting techniques, a hardware assessment technique, and a dynamic translation technique. We additionally compare with 2 compiler-based techniques as reference. Due to time limitation, I will discuss 3 experiments. Much more can be found in our paper. The first experiment is about the fuzzing efficiency, and the experiment is conducted on Google FTS. We first present the result on some programs. We take AFL GCC as a baseline and report the ratio of each tool to AFL GCC. If the ratio is 0, it means the tool cannot handle the program. Larger number indicates better performance. Different color denotes different tools in each bar chart from the left to right. They are for AFL GCC, which is always 1, AFL CloneFast, AFL QML, PTFuzzer, inline patch, data log disassembling, and STOCHFUZZ. Let's look at the OpenSSL result. We can see inline patch and data log disassembling both fail on rewriting it due to their unsoundness. In fact, existing static rewriting technique all fail on some program in Google FTS, while STOCHFUZZ succeeds on all of them. Then let's look at the JSON result. We observe that AFL CloneFast is the fast one as it is the IR-based technique. STOCHFUZZ is slightly slower due to our additional overhead. Data log disassembling also perform well, but note that due to its unsoundness, it fails on many programs. The other 3 techniques are relatively slower. We present the average execution number over 24 programs. We can see that compared with AFL CloneFast, STOCHFUZZ only has around 11% slowdown on average. Other tools have higher overhead compared with STOCHFUZZ. Programs built by popular compiler may not contain substantial code and data interleaving. So we modify the compilation of Google FTS to force read-only data to be interleaved with text section. We then study how the number of intentional crash and unintentional crash, false positive and false negative change over fuzzing. The trending is showing on the right. The blue curve is for intentional crash, while the yellow curve is for the unintentional crash. The red curve is for the false negative rate, while the green curve is for the false positive rate. Observe that the blue curve almost reaches its fixed point after 5 minutes, indicates that the whole process almost converged at the first 5 minutes. As such, we can say that the overhead caused by the incremental rewriting is negligible. Also observe that the number of unintentional crash is very small compared with the intentional crash. Note that the unintentional crash may trigger more expensive repair process. It implies that most rewriting errors are fixed by observing new coverage. iJoin is a state-aware fuzzing technique which increases fuzzing effectiveness by observing how the value of given variable change. Let's look at a simple example. The code contains a while loop. Inside the while loop, there is an if-else statement. For AFL, to connect code coverage, the compiler instrument has 3 points. All of them are the starting points of basic blocks. Compared with AFL, iJoin automatically connects the value of x and y, which makes the fuzzer observe more state. We port iJoin to support binary-only fuzzing based on AFL QML and STOCHFUZZ, and conduct the same maze experiment in the iJoin paper. The result shows that STOCHFUZZ is around 8 faster than AFL QML. Additionally, STOCHFUZZ only has around 8% slowdown compared with the source-based iJoin. I will skip the related work due to time limitation. More can be found in our paper. So as a result, we develop a new fuzzing technique for strict binary. Okay, it's the end of my presentation. Thank you for your time. Our session is available online, and you can reach me at the shown email address.